Picture this extraordinary scenario. You're standing in your backyard on a clear evening, tossing a ball straight up into the air. According to everything we understand about physics and gravity, that ball should reach its peak height and then fall back into your waiting hands. But imagine if something completely unexpected happened. Instead of falling back down, the ball keeps going up, moving faster and faster until it disappears into the darkening sky. This mind-bending scenario perfectly illustrates what astronomers discovered about our universe in 1998, when they unveiled one of the most profound mysteries in modern science: dark energy. This discovery fundamentally transformed our understanding of the cosmos and challenged everything we thought we knew about the universe's behavior. For decades, scientists had believed that the universe's expansion, set in motion by the Big Bang, would gradually slow down due to gravity's relentless pull. Just as gravity pulls that ball back to Earth, they expected the collective gravitational force of all matter in the universe to act as a cosmic brake, eventually bringing the expansion to a crawl. However, when astronomers studied distant supernovae, massive stellar explosions that serve as cosmic distance markers, they found something that defied all expectations. Not only was the universe continuing to expand, but it was doing so at an accelerating rate. It was as if some mysterious force was pushing everything apart with increasing strength, overwhelming gravity's attempt to pull things together. This force, which we now call dark energy, pervades every cubic centimeter of space and becomes more dominant as the universe grows larger. Today, we stand at the threshold of one of science's greatest adventures. We're working to understand a force that makes up approximately 68% of everything in our universe, yet remains largely mysterious to us. It's a force so powerful that it's literally shaping the destiny of our cosmos, determining whether the universe will continue expanding forever or meet some other cosmic fate. The quest to understand dark energy has united scientists across the globe in one of the most ambitious scientific endeavors ever undertaken. Through powerful telescopes, sophisticated satellites, and groundbreaking experiments, we're slowly piecing together clues about this enigmatic force. Every new discovery brings us closer to understanding not just how our universe works, but perhaps why it exists in the form we observe today. As we embark on this fascinating journey together, we invite you to join our growing community of cosmic explorers. By subscribing to our channel, you'll be part of a passionate group of individuals who share a common curiosity about the universe's deepest mysteries. Together, we'll explore the cutting-edge science behind dark energy, discuss the latest discoveries, and contemplate what they mean for our understanding of reality itself. The universe has presented us with an incredible puzzle, and solving it may revolutionize our understanding of space, time, and existence itself. When Albert Einstein first applied his revolutionary theory of general relativity to the entire cosmos in 1917, he encountered what he considered a serious problem. His equations suggested something that seemed impossible at the time. The universe should be either expanding or contracting. This contradicted the prevailing belief of the era that the universe was eternal and unchanging. Einstein, despite his reputation for revolutionary thinking, couldn't bring himself to accept this implication of his own theory. To resolve this apparent conflict, Einstein introduced what he would later call his biggest blunder: the cosmological constant. This mathematical term was essentially a fudge factor added to his equations, designed to create a repulsive force that would exactly balance gravity's attractive force, resulting in a static universe. It was a brilliant mathematical solution to what turned out to be a non-existent problem. Everything changed in 1929 when Edwin Hubble provided observational evidence that galaxies were moving away from each other, proving the universe was actually expanding. This discovery led to the development of the Big Bang theory, first proposed by Georges Lemaitre, who suggested that if galaxies were moving apart, they must have been closer together in the past. Following this logic backward in time led to the conclusion that the universe had a beginning, a moment of incredible density and temperature from which everything expanded. According to the classical understanding that emerged, the universe's expansion should have been gradually slowing down. The reasoning was straightforward and seemed almost obvious. Gravity, being an attractive force, should be pulling all matter back together, acting like a cosmic brake on the expansion. Imagine throwing a handful of marbles into the air. Gravity inevitably slows them down and brings them back. Similarly, scientists expected the combined gravitational pull of all the matter in the universe to be slowly, but surely decreasing the expansion rate. This model of cosmic evolution was so well established that it became the foundation for numerous calculations and predictions about the universe's future. Astronomers debated whether there was enough matter in the universe for gravity to eventually stop the expansion completely, leading to a big crunch, or whether the expansion would continue forever, gradually slowing but never quite stopping. The question wasn't whether the universe's expansion was slowing down. That seemed certain, but rather how quickly it was slowing and what the ultimate fate of the universe would be. The mathematics was solid, the physics made perfect sense, and everything aligned with our understanding of gravity and matter. It created a beautifully consistent picture of a universe that began with an explosive expansion, which would inevitably be tamed by gravity's relentless pull. This was more than just an elegant theory. It was supported by everything we knew about physics and seemed to be one of the few certainties in cosmology. Yet nature had a surprise in store that would turn this entire picture on its head. The universe, as we would discover, had other plans that would force us to fundamentally rethink our understanding of space, time, and the very nature of reality itself. But perhaps most importantly, it would remind us of a crucial lesson in science. Even our most cherished and well-supported theories must ultimately bow to observational evidence, no matter how unexpected or revolutionary that evidence might be. In the late 1990s, two independent teams of astronomers set out on what would become one of the most significant quests in scientific history. The Supernova Cosmology project, led by Saul Perlmutter, and the High-Z Supernova Search Team, headed by Brian Schmidt and Adam Rees, were both pursuing the same ambitious goal: measuring the universe's expansion rate with unprecedented precision. These teams focused their attention on a particular type of stellar explosion, known as Type 1a supernovae. What makes these cosmic explosions so special is their remarkable consistency. Type 1a supernovae occur when a white dwarf star in a binary system accumulates enough matter from its companion to reach a critical mass, approximately 1.4 times the mass of our Sun. At this precise threshold, the white dwarf undergoes a catastrophic explosion, releasing an almost identical amount of energy every time. This consistency makes Type 1a supernovae perfect standard candles, cosmic distance markers that shine with a known intrinsic brightness. The logic behind using these stellar explosions was straightforward. By comparing how bright these supernovae appear from Earth with their known intrinsic brightness, astronomers could calculate their precise distances. Combined with measurements of how fast these galaxies were moving away from us, this data would reveal how the universe's expansion rate had changed over time. What happened next shook the foundations of physics. According to all existing theories, the universe's expansion should have been slowing down under the influence of gravity. Therefore, distant supernovae should have appeared brighter than expected, as they would have been closer to us than their current recession velocities would suggest. However, both teams found exactly the opposite. The distant supernovae were consistently dimmer than they should have been, indicating they were farther away than anticipated. This observation led to an astonishing conclusion. Not only was the universe's expansion not slowing down, but it was actually accelerating. Something was pushing the cosmos apart with ever-increasing force, overwhelming gravity's attractive pull. This mysterious cosmic repulsion would soon become known as dark energy. Prior to this groundbreaking discovery, cosmologists had worked within a framework where gravity was the dominant force shaping the universe's evolution. They debated whether the universe would eventually collapse under gravity's pull or continue expanding forever, gradually slowing down. Some had even revisited Einstein's cosmological constant, which he had originally introduced to create a static universe, but most viewed it as an unnecessary complication. The discovery of cosmic acceleration fundamentally transformed our understanding of the universe. It revealed that about 68% of the cosmos consists of this enigmatic dark energy, making it the dominant component of our universe. This discovery was so revolutionary that it earned Perlmutter, Schmidt, and Rees the 2011 Nobel Prize in Physics. When we look at the graphs comparing the expected versus observed brightness of these distant supernovae, we see a clear divergence from predictions. The dimmer appearance of distant supernovae creates a distinct curve that deviates from what we would expect in a universe dominated by gravity alone. This simple yet profound difference represents one of the greatest scientific discoveries of the 20th century and continues to challenge our understanding of fundamental physics. The implications of this discovery reach far beyond astronomy. It suggests that the very fabric of space itself possesses some intrinsic energy that causes it to expand. This concept forces us to reconsider everything from the nature of empty space to the ultimate fate of our universe. What was once thought to be empty vacuum may actually be teeming with some form of energy that we are only beginning to understand. Dark energy stands as one of the most enigmatic phenomena in modern cosmology, possessing characteristics that challenge our fundamental understanding of physics. Let's delve into its fascinating properties that make it such a unique force in our universe. Perhaps the most remarkable feature of dark energy is its uniform distribution throughout space. Unlike matter, which clumps together under gravitational forces to form galaxies and cosmic structures, dark energy maintains a constant density everywhere. Whether we examine the space between galaxies or the vast cosmic voids, dark energy remains perfectly smooth and homogeneous. This uniformity means that every cubic centimeter of space, whether in our solar system or in the most distant reaches of the cosmos, contains exactly the same amount of dark energy. One of dark energy's most counterintuitive properties is its negative pressure effect. In conventional physics, we typically think of pressure as a force that pushes things together. However, dark energy exhibits a negative pressure that effectively acts as a repulsive force. This negative pressure creates a sort of anti-gravity effect, pushing space itself to expand rather than contract. As the universe expands, instead of becoming diluted like normal matter or radiation, dark energy maintains its constant density. This means that as space grows larger, the total amount of dark energy in the universe actually increases, leading to an ever-accelerating expansion. The sheer abundance of dark energy in our universe is staggering. Current measurements indicate that dark energy comprises approximately 68% of the total energy content of the observable universe. To put this in perspective, all the visible matter that makes up the stars, planets, galaxies, and interstellar gas accounts for only about 5% of the universe's content. The remaining 27% consists of dark matter, another mysterious component that we can detect through its gravitational effects but cannot directly observe. This distribution means that the force driving our universe's acceleration is not just a minor player, but the dominant component of our cosmic reality. The implications of these properties are profound. As the universe continues to expand, the influence of dark energy grows ever stronger. While the density of matter decreases as space expands, dark energy's constant density means its effects become increasingly dominant over time. This leads to some startling predictions about our universe's future, where galaxies may become so distant from each other that they effectively become isolated islands in an ever-expanding cosmic ocean. Scientists are particularly intrigued by how dark energy's properties align surprisingly well with Einstein's cosmological constant, which he originally proposed as a mathematical term to create a static universe. However, the observed value of dark energy's strength is vastly smaller than quantum physics predicts it should be, creating one of the most significant discrepancies in modern physics. This mismatch between theory and observation continues to drive research and spark new ideas about the fundamental nature of space, time, and energy. The quest to understand dark energy has spawned some of the most ambitious scientific projects in human history. Modern research combines cutting-edge observational technology with sophisticated theoretical frameworks, creating a multi-pronged approach to unveiling the nature of this cosmic mystery. The Dark Energy Survey, conducted from 2013 to 2019 at the Cerro Tololo Inter-American Observatory in Chile, represents one of our most comprehensive efforts to map the universe's structure. Using a 570-megapixel digital camera mounted on a 4-meter telescope, this groundbreaking survey captured images of hundreds of millions of galaxies across 1/8 of the entire sky. The project's primary aim was to track how the distribution of galaxies has changed over cosmic time, providing crucial data about how dark energy has influenced the universe's evolution. By measuring subtle distortions in the shapes of distant galaxies, a phenomenon known as weak gravitational lensing, scientists can map both visible and dark matter distributions across vast cosmic distances. The European Space Agency's Euclid Space Telescope, launched in 2023, marks a new era in dark energy research. This sophisticated space observatory is designed to create a three-dimensional map of the universe, observing billions of galaxies out to 10 billion light-years. Euclid's primary mission is to understand why the universe's expansion is accelerating and whether this acceleration changes over time. The telescope employs two primary instruments, a visible light camera and a near-infrared spectrometer and photometer. These tools allow scientists to measure the precise shapes and distances of galaxies with unprecedented accuracy, providing vital clues about how dark energy has shaped cosmic structures throughout history. The Nancy Grace Roman Space Telescope, scheduled for launch in 2027, will bring even more powerful capabilities to dark energy research. Formerly known as WFIRST, this NASA mission will feature a primary mirror the same size as Hubble's, but with a field of view 100 times greater. This wide-field capability will enable the telescope to survey large portions of the sky quickly, collecting data on billions of galaxies. The Roman telescope will employ multiple techniques to study dark energy, including observing Type Ia supernovae as standard candles and measuring the clustering patterns of galaxies across different cosmic epochs. On the theoretical front, scientists are exploring various hypotheses to explain dark energy's nature. One prominent theory suggests that dark energy might be a property of space itself, similar to Einstein's cosmological constant. According to this view, even empty space contains an intrinsic energy that drives cosmic expansion. Another intriguing possibility is the quintessence theory, which proposes that dark energy is a dynamic field that varies across time and space, potentially explaining why its observed strength differs so dramatically from quantum physics predictions. Some researchers are exploring even more exotic possibilities, such as modified gravity theories that suggest our understanding of gravitational forces might need revision on cosmic scales. Others investigate the potential connection between dark energy and extra dimensions, drawing inspiration from string theory and other unified physics frameworks. Advanced computer simulations play a crucial role in testing these theories. Scientists use supercomputers to model how different forms of dark energy would affect the universe's evolution, creating virtual universes that can be compared with observational data. These simulations help constrain theoretical models and guide future observational strategies. Machine learning and artificial intelligence are increasingly important tools in dark energy research. These technologies help scientists analyze the massive datasets generated by modern surveys, identifying subtle patterns and correlations that might otherwise go unnoticed. They're particularly valuable in processing the complex imagery from gravitational lensing observations and in identifying distant supernovae for follow-up study. The combination of these observational and theoretical efforts represents humanity's most sophisticated attempt to understand the fundamental nature of our universe. As new data continues to flow in from these various projects, scientists hope to narrow down the possible explanations for dark energy and perhaps unlock one of the greatest mysteries in modern physics. When discussing the ultimate fate of our universe, scientists present us with several fascinating possibilities, each directly influenced by dark energy. The first scenario is the Big Freeze or heat death, where the universe continues expanding eternally, with galaxies growing ever more distant from each other until they become completely isolated. Another possibility is the Big Rip, where dark energy becomes so powerful that it eventually tears apart galaxies, solar systems, planets, and even atoms themselves. A third scenario suggests that dark energy might change its behavior over time, potentially leading to a big crunch if it reverses its current expansive effect. These scenarios prompt us to consider profound questions about our cosmic destiny. What will happen to life and civilization in a universe dominated by dark energy? Will intelligent life eventually become confined to isolated galactic islands, unable to communicate with or reach other parts of the cosmos? These questions highlight the deep connection between our understanding of dark energy and our species' ultimate fate. The discovery of dark energy fundamentally transforms our perspective on the universe in several ways. First, it reveals that empty space isn't truly empty, but contains an intrinsic energy that shapes cosmic evolution. This challenges our intuitive understanding of nothingness and suggests that the vacuum itself is a dynamic entity. Second, it demonstrates that the visible universe, the stars, galaxies, and clusters we can see, represents only a tiny fraction of what exists. This humbling realization forces us to acknowledge how much we still have to learn about our cosmic home. Furthermore, dark energy's discovery reminds us that the universe can still surprise us with phenomena that completely contradict our expectations. It teaches us intellectual humility and the importance of remaining open to new ideas, even when they challenge our most basic assumptions about how the universe works. When it comes to explaining dark energy to someone using everyday analogies, several compelling comparisons can help illuminate its nature. Imagine a balloon being inflated. The surface represents our three-dimensional space expanding. Now, instead of the air pressure inside the balloon driving the expansion, imagine that the rubber itself has some intrinsic property that makes it stretch automatically. This is similar to how dark energy appears to be an intrinsic property of space itself. Another helpful analogy involves thinking about a loaf of raisin bread rising in the oven. As the dough expands, the raisins, representing galaxies, move apart from each other. Dark energy is like an endless supply of yeast that continues to make the dough expand faster and faster, rather than the expansion slowing down as you might expect. For a more dynamic analogy, consider a group of friends playing with magnetic toys. If the magnets are oriented to repel each other, they push apart with a force that increases as they get closer together. Dark energy works in the opposite way. Its repulsive effect becomes stronger as things get farther apart, contrary to our everyday experience with forces like gravity and magnetism. These analogies, while imperfect, help illustrate different aspects of dark energy's behavior. They provide accessible entry points for understanding this complex phenomenon and can spark fascinating discussions about the nature of space, energy, and the universe itself. The challenge of explaining dark energy also highlights an important aspect of scientific communication: the need to bridge the gap between complex physical concepts and everyday experience. When we encourage people to create their own analogies for dark energy, we not only help them understand the concept better, but also engage their creativity and critical thinking skills. This process of creating analogies can lead to deeper insights and new ways of thinking about cosmic phenomena. Through these interactive elements, contemplating the universe's fate, considering how dark energy changes our perspective, and creating accessible analogies, we can better engage with one of science's greatest mysteries while developing a deeper appreciation for the complexity and wonder of our cosmos. The nature of dark energy raises profound questions about the ultimate destiny of our universe, leading scientists to explore several possible scenarios that could unfold over the coming billions and even trillions of years. At the heart of these investigations lies the fundamental question: will the universe's expansion continue forever? Current observations suggest that the expansion is not only continuing but accelerating, driven by dark energy's mysterious influence. If dark energy maintains its present properties, the expansion will indeed continue eternally. This scenario paints a rather lonely picture of the cosmic future, where galaxies become increasingly isolated as the space between them expands faster than light can travel. Eventually, civilizations might find themselves permanently cut off from most of the observable universe, confined to their local galactic neighborhoods. However, the possibility that dark energy's properties might change over time adds another layer of complexity to this cosmic narrative. If dark energy's strength increases over time, we might face an even more dramatic scenario known as the Big Rip. This fascinating yet unsettling possibility suggests that the accelerating expansion could become so violent that it literally tears the universe apart. The Big Rip scenario unfolds like a cosmic countdown to destruction. As dark energy's influence grows stronger, larger and larger structures begin to break apart. First, galaxy clusters would be torn asunder, their member galaxies flung apart by the overwhelming expansive force. Next, individual galaxies would disintegrate as their stars are scattered into the expanding void. Solar systems would follow, with planets being ripped away from their parent stars. In the final moments, even atoms themselves would be unable to hold together against the ultimate cosmic force. Scientists have actually calculated potential timelines for such a scenario. If the Big Rip is our universe's fate, the process might begin with the dissolution of galaxy clusters about 1 billion years before the final moment. Individual galaxies might start breaking apart about 60 million years before the end. In the last few minutes, planets would shatter, and in the final tiny fractions of a second, atomic nuclei would split apart. The impact on cosmic structures presents another fascinating area of study. We're already observing how dark energy affects galaxy cluster formation and the large-scale structure of the universe. As space expands at an accelerating rate, it becomes increasingly difficult for gravity to pull matter together into new cosmic structures. This means that the universe we observe today might represent the peak of cosmic structure formation. In the distant future, existing galaxies will continue to evolve, but the formation of new galaxy clusters will become increasingly rare. Star formation will gradually slow as galaxies exhaust their gas supplies, and the expansion of space makes it harder for remaining gas clouds to collapse into new stars. The universe will slowly transition from its current state of vibrant activity to one of increasing isolation and darkness. The effects on individual galaxies are particularly intriguing. While our Milky Way and its nearest neighbor Andromeda are still expected to merge in about 4.5 billion years due to their gravitational attraction, more distant galaxies will become permanently unreachable. The observable universe will gradually shrink from our perspective as more and more distant regions accelerate beyond our cosmic horizon. These scenarios raise profound implications for the future of life and intelligence in the universe. If civilizations survive long enough, they might need to develop strategies to cope with an increasingly isolated cosmic environment. The challenges of conducting astronomy and understanding the universe's nature will become progressively more difficult as fewer galaxies remain observable. The study of these questions extends beyond pure scientific curiosity. Understanding the universe's ultimate fate helps us grasp our cosmic context and place in time. It reminds us that the universe we observe today is just one frame in an ongoing cosmic evolution, and that the changes driven by dark energy will eventually transform the night sky into something very different from what we see today. Moreover, these investigations push the boundaries of our physics theories, forcing us to consider whether our current understanding of gravity, quantum mechanics, and the nature of space-time itself might need revision. The answers to these big questions about dark energy and the universe's fate might ultimately lead to revolutionary new insights about the fundamental nature of reality itself. Dark energy research has become a powerful driver of technological innovation, pushing the boundaries of what's possible in multiple scientific fields. The quest to understand this mysterious force has led to remarkable advances in detector technology, particularly in the development of increasingly sensitive astronomical instruments. The cameras developed for dark energy surveys have pioneered new frontiers in digital imaging, with applications extending far beyond astronomy. For instance, the dark energy camera, with its 570-megapixel array, sparked innovations in sensor technology that have influenced medical imaging and industrial inspection systems. The computational demands of processing vast amounts of astronomical data have spurred developments in big data handling and analysis techniques. Scientists working on dark energy surveys have developed sophisticated algorithms and machine learning tools that are now being applied in fields ranging from climate modeling to financial analysis. The need to store and process petabytes of observational data has driven advances in data management systems and cloud computing architectures. The precision requirements of dark energy measurements have also revolutionized our approach to calibration and error correction in scientific instruments. These advances have found applications in various industries, from precision manufacturing to quality control systems. The techniques developed to remove atmospheric distortion from astronomical images have been adapted for use in satellite imaging, medical scanning, and even facial recognition technology. In terms of fundamental physics, dark energy has profoundly impacted our understanding of the universe's basic principles. It has forced us to reconsider our most fundamental theories about gravity, space, and time. The discovery challenges the compatibility between quantum mechanics and general relativity, two pillars of modern physics that seem to disagree about the nature of dark energy. This contradiction has sparked new theoretical approaches and potentially revolutionary ideas about the nature of space-time itself. The existence of dark energy suggests that empty space is far from empty, containing an intrinsic energy that influences cosmic evolution. This realization has led to new investigations in quantum field theory and has revitalized interest in modified gravity theories. The discrepancy between the observed value of dark energy and quantum mechanical predictions has become known as the cosmological constant problem, considered one of the most significant challenges in theoretical physics. Looking toward humanity's future in space, dark energy plays a crucial role in shaping our long-term prospects for space exploration and colonization. The accelerating expansion of the universe, driven by dark energy, means that there may be a finite window of opportunity for interstellar travel. As galaxies move apart at ever-increasing speeds, reaching distant star systems will become progressively more challenging. This realization has important implications for space exploration strategies and the timeline for potential human expansion into space. It suggests that if humanity aims to explore beyond our local galactic group, we may need to act within a cosmic window of opportunity before dark energy's effects make such journeys impossible. The study of dark energy also influences our understanding of habitable zones on a cosmic scale. As we search for potential new homes among the stars, we must consider how dark energy's influence on cosmic structure formation affects the distribution and evolution of galaxies suitable for life. This knowledge becomes crucial for long-term planning of human expansion into space. Furthermore, dark energy research has contributed to the development of space-based observatories and measurement techniques that will be essential for future space navigation and exploration. The precise mapping techniques developed for dark energy surveys have improved our understanding of cosmic geography, which will be crucial for plotting future interstellar journeys. Perhaps most profoundly, dark energy research reminds us of our unique position in cosmic history. We live in an era where we can still observe and study distant galaxies before they accelerate beyond our view. This understanding creates a sense of urgency in our scientific endeavors and highlights the importance of preserving and advancing our knowledge for future generations. As we continue to unlock the mysteries of dark energy, we're not just learning about the universe's fate, we're helping to chart the course for humanity's future among the stars. From a seemingly routine observation of distant stellar explosions, we embarked on a journey that has fundamentally transformed our understanding of the cosmos. The discovery of dark energy stands as a testament to science's power to reveal profound truths that challenge our most basic assumptions about reality. Like Einstein's revelation that space and time are intertwined, or the quantum mechanical insight that particles can exist in multiple states simultaneously, dark energy has forced us to reimagine the very fabric of our universe. This journey of discovery reminds us that even in an age of unprecedented technological advancement, the universe continues to surprise and humble us. The fact that roughly 68% of our cosmos consists of an energy we barely understand highlights both the breadth of our ignorance and the exciting frontiers that await exploration. Dark energy's discovery serves as a powerful reminder that some of the most significant breakthroughs in science come not from confirming what we expect to find, but from having the courage to accept what we actually observe, even when it defies our expectations. As we stand at this frontier of human knowledge, we find ourselves in a unique position in history. We are the first generation to know about dark energy's existence, yet we may be far from the last generation to grapple with its mysteries. The questions raised by this discovery will likely engage the minds of scientists, philosophers, and curious individuals for decades, if not centuries, to come. The story of dark energy also teaches us an invaluable lesson about the nature of scientific inquiry itself. It shows how careful observation, combined with intellectual honesty and rigorous analysis, can lead us to discoveries that completely revolutionize our worldview. It reminds us that the universe is often stranger and more fascinating than our limited human imagination might suggest. As we conclude this exploration, we should remember that every great scientific discovery not only answers existing questions, but also opens up new avenues of inquiry. Dark energy is no exception. Its discovery has spawned new fields of research, driven technological innovation, and raised profound questions about the nature of space, time, and the very destiny of our universe. Our journey together doesn't end here. We invite you to become part of our growing community of cosmic explorers by subscribing to Exploring the Universe. This vibrant community brings together individuals united by their curiosity about the cosmos and their desire to understand its deepest mysteries. By joining us, you'll gain access to regular updates on the latest discoveries in cosmology, detailed explorations of fascinating astronomical phenomena, and opportunities to engage with fellow space enthusiasts. Remember that when you gaze at the stars, you're not just observing distant points of light. You're witnessing the interplay of mysterious forces that shape our cosmic destiny. Every new question you ask, every moment of wonder you experience, adds to humanity's great adventure of cosmic discovery. Don't miss out on our upcoming explorations. Subscribe now to ensure you receive notifications about new episodes, exclusive content, and opportunities to engage with our community of cosmic explorers. Together, we'll continue to push the boundaries of human knowledge and understanding, one discovery at a time. The mysteries of the cosmos await, and your journey of discovery is just beginning. Join us as we explore the greatest questions humanity has ever asked and search for answers in the vast expanse of space and time. The universe is calling. Will you answer?